In the series of discussions of chemical thermodynamics, today I shall try to develop the Maxwell's relations and their applications with some examples to clarify the subject. And in thermodynamics, already we have known there are four energy terms. Energy parameters, and internal energy, enthalpy, entropy, work function, and free energy, gives free energy. These are all energy terms. And also there are variable parameters. Variable parameters are pressure, temperature, and volume, and entropy. Yes. These are the variable parameters. These are the energy parameters. Today I shall try to relate all these parameters of a system which is at equilibrium, and these relations or these interrelations are known as Maxwell's relations. And these Maxwell relations, before going to these Maxwell relations, we can remember the four basic thermodynamic equations. Basic thermodynamic equations, basic thermodynamic equation. And one is du equal to TdS minus Pdv, and the second one dH equal to TdS plus Vd, and the third one dA equal to Td minus SdT minus Pdv, and the fourth one is dJ equal to minus SdT and plus Vd, and these are the basic thermodynamic equations. And the basic thermodynamic equations are very much helpful to formulate these Maxwell relations and other parts of this thermodynamics. And each basic thermodynamic equation gives rise to one Maxwell's relation. So altogether we shall get these four Maxwell's relations. So let us consider the first one, how the Maxwell's relations could be formulated by using this first basic thermodynamic equation. And say du equal to T dS minus Pdv, and at a constant volume, we can write del U by del S at constant volume equal to minus P. Again differentiating. Differentiating with respect to V at a constant S. We get del by del V, and it is del U by del S at constant V, and this one at constant S. This will give you minus del P divided by del V at constant S. Again, this equation at a constant entropy, this equation will give del U by del V at constant entropy. This one equal to at constant V, this one at constant entropy, this one del U by del S, it is T, and this one is T. So dU equal to TdS minus PdV, and at constant volume this one becomes a 0. So del U by del S equal to T. Again differentiating with respect to V at constant S, we get this del T by del V at constant S. At a constant S again, but this one becomes a 0. So this del U by del V at equal to minus P. Again differentiating with respect to entropy at a constant volume. At constant volume, we shall get del U by del S, and here del U by del V at constant S, and here at constant V equal to minus del V by del S at a constant V. So this, since this U is a state function, it will obey the Euler's reciprocal relation, and so left hand side of this 2 will be the same as for the state function. It is immaterial for the sequence of this variables with which this differentiation is being done. So this left hand side equal, then right hand side also becomes equal. So equating, then right hand side becomes equal, and we get the relation del T by del V at constant S equal to minus del P divided by del S at a constant V. So this relation, this basic equation gives this sort of relations. So whether we can put a generalized formulation. generalized formulation. For getting the Maxwell's relations from each of these basic equations. So general formulation is that suppose z is a function of x and y, then dz equal to del z by del x and y, and it is the dx plus del z divided by del y, and here x, and it is dy. Let this term is n dx, and this term is n dy. Then this n equal to del z by del x, and it is y. So again differentiating del m by del y, keeping x fixed, equal to del to z or del by del y, and here del z divided by del x and y, and this x. And similarly, this n equal to this one, del z divided by del y and constant x, or del n divided by del x, keeping this constant y, equal to del by del x, and here del z divided by del y, and here x, and it is y. Since z is a difference, z is state function, it will obey the Euler's theorem. So this one and this one will be the same. So left hand side, these two left hand sides also be the same. So from this equation, if this one is the equations, then I can write if dz equal to m dx plus m dy, then the relation becomes del m divided by del y, and keeping x fixed, equal to del n divided by del x, and keeping y fixed. If this is the equation, this will be the relations. So in that case, I can also write the from this second one, del t by del p at constant s, equal to del v divided by del s at a constant p. And from this equation, again del p divided by del t at a constant del t, del s by del t at constant v, equal to del s divided by del v at constant t. And from this equation, again del v by del t equal to at constant p, and this one will give this del s divided by del p at constant each relation, each basic thermodynamic equation gives rise to one Maxwell relation. So these are the four Maxwell relations. This is 1, and this is 2, and this is 3, and this is 4. In order to, you can see, if you see the relations, then left hand side of this relation is measurable. S is constant, means whenever the process is reversible adiabatic, S is fixed, here V is fixed, here P is fixed. So each of this left hand side could be measured by means of the suitable instrument, while the right hand side contains this entropy, and entropy could not be measured. No such instrument is there to determine this entropy of a system. So right hand side is the non-measurable quantities. So these relations are the excellent device to measure these unmeasurable quantities in terms of these measurable quantities. And in order to remember, actually these relations are very important, and it requires very instant in while you are deriving this any relation. So you have to remember this one. And for that purpose, actually conic bond diagram is very popular. Conic bond Maxwell is very popular to memorize all these four relations. Here I shall give another tricks to determine, to find out these relations very easily. Suppose let us consider one circle. And this circle, here S, P, T and P. These are the variable parameters. Suppose we like to determine these relations, find out these relations. If we try to find out to find out this relation, then it is coming from T to B, means coming from T, this one arrow, it is a clockwise arrow. So here PS, so TB, and so in this case also it will be arrow. If it is clockwise, then it is anti-clockwise. Then actually del T by del V, numerator T, del T, denominator B, del V, and here it is del P and by del S. Here V is constant, here S is constant. And one thing to remember, whenever the SP remains in this numerator and denominator, then negative sign, this term will contain this negative term. Jokingly I can say this SP means superintendent of police, very powerful person. So in order to combat that person, one negative sign is to be given. Then if we like to this one, then TP, then this arrow is starting from T and ending at P. So this arrow just diagonally opposite in the opposite directions, and so this one again arrow. So this del T by del P, here del V by del S, del V by S, no SP, so no negative sign, and P here and S here, constant. And this third one, P versus PT. PT means PT, then it will be this one, PT. then del P by del T equal to del S by del V and V here and T here are constants. Then fourth one V2T and V2T and here also S2P, diagonally opposite. So V2T equal to here del S by del P and P here and P here, SP in the numerator and denominator present, so one negative sign. So this is very easy to memorize all these four relations. Formerly I have seen in my childhood this English word, very complicated word, very difficult to spelling. So in that case, this sort of method is used. Say suppose lieutenant. What will be the spelling of this lieutenant? Very cute terms. In that case, we use the in Bengali mithe tumi dos pipre. Mithe means li, tumi means you, dos means 10, pipre a. So this will be the spelling of this lieutenant in Bengali. So by this way also I have taken this device to memorize this one. Among these relations, it is to be remembered, these two relations are not referred to any process. These are the relations for the system whenever it is in equilibrium. And particularly 3 and 4, these two relations are very important. You can see this suppose equation relation 3. Relation 3. Here del S by del V at constant temperature equal to del P by del T at a constant V. So this term is measured experimentally. You can determine keeping the volume of constant. What will be the increase of pressure by increase of 1 degree temperature. So whenever this is known by experiment, this could be determined. And you can see this one is positive. If you for a system, for a gaseous system, if you find an equation of state, then from this equation of state you can also calculate this one, and this calculation will give you the variations of this entropy with this volume at a constant temperature. Means isothermal variation of entropy with the volume could be obtained by putting a suitable equation of state and calculating this one for that gas. And this one is positive. With the rising T, P must increase. It means that whenever you increase this V, then S will also increase. Means with this increase of volume of any system, the entropy or the randomness of the system will increase. And from this one also I can refer this minus del S by del P, or here equal to minus del V by del T at a constant pressure. This one also could be determined experimentally with keeping the constant pressure constant for a gas, increasing volume with a rise in 1 degree temperature. Or if we have a suitable equations for that gas, then we can calculate this value, and which will give the pressure dependency of entropy. And this one actually negative. This one positive, and here negative signs, so negative that means whenever P is increased and S is decreased. What does it mean? With this increase of pressure, the entropy or the randomness of the system must decrease. So these are the four relations having certain utility, and now I write the applications of the Maxwell's relations. Application of Maxwell relations. It is the formulation of thermodynamic equation of state. Equation of state, and there are, or it is sometimes also called energy equations. We have actually thermodynamic equation of state 1. Let us start with the basic thermodynamic equations. du equal to T dx and minus PdV. This is the first basic thermodynamic equations in terms of this internal energy. So if we keep dividing by, it is dividing by dV at a constant t, we get del u by del v at constant t equal to t is constant, del s by del v at a constant temperature and minus p. And this equation is not a measurable quantity, so this term could be transformed into some measurable quantity by the use of this Maxwell's relations. Maxwell's relation is like that: S P T V and S to V, and so P to T. So these relations will be del S by del V, and this one equal to del P divided by del T, and T coming here constant, V here coming constant. So instead of this term, I can write this one. So this relation becomes del U by del V at constant temperature equal to T into del P divided by del P at constant volume minus P. So this one actually the first thermodynamic equation of state, and from this, if we calculate for this ideal gas, this one actually they call the internal pressure. This one is called internal pressure of this substance in the system. So this relation, from this relation we can conclude for ideal gas, for ideal gas, if we calculate this one, for ideal gas, this relation is V equal to RT for, or N RT for 1 mole of this gas, And if we do here calculations, del P by LT, differentiating pressure with respect to temperature at constant volume and minus P, then you can see this del U divided by del V at constant temperature equal to 0. It means that U is a function of a temperature only and does not depend on this volume. And this internal pressure is coming from internal forces among the constituent particles in the system. Since for this ideal gas this term is equal to 0, means interpressure equal to 0. So for ideal gas there is no intermolecular attractions or internal forces existing among the molecules. And for van der Waals gas, the equation is P plus A N square by V square into V minus NV equal to N RT. If we do calculations, this one multiplied by T minus P, then it will be del U by del V at constant temperature equal to A N square by V square. So this internal energy is a function of. So this internal energy is a function of for van der Waals gas T and also V. And that means this one is the positive. What does it mean? Whenever the van der Waals gas expands, its internal energy will also increase. Whenever the expansion occurs at constant temperature, its internal energy will also increase. Internal energy will also increase. So this for the substances other than the ideal gases, this internal pressure, having the very low value. Actually, V is very large, A is small. So this value is small, relatively small, but definitely non-zero, and its value, internal pressure, having a non-zero value and relatively small for these gases, real gases, but it is very much high for this liquid. In case of liquid, volume is very small, A is very large, so this value will also be very large. So this term also I can express in terms of this alpha and beta. Alpha equal to 1 by V into del V by del P at a constant pressure, and it is called cubical. Alpha is called cubical expansion coefficient of the system, and beta equal to minus 1 by V del V by del P at a constant temperature. So this beta is actually isothermal temperature constant, isothermal compressibility coefficient of the system. So if we do calculations alpha by beta, is equal to, we get del P by del T at a constant value. This one I have shown while formulating the Cp minus Cv for the gases, for the substances in terms of this alpha and beta. So this form, this internal energy del U by del V at constant temperature, you can write this one alpha T by beta and minus P, or this one equal to alpha T minus beta P and divided by beta. So this term also we calculated if we know the alpha and beta and temperature pressure of this system. Similarly, second thermodynamic equations. Second thermodynamical equation of state or you can say this energy equation. So in this case dH equal to TdS and plus VdP. Again dividing by dP at constant temperature, we get del H by del P at constant temperature equal to T constant and del S by del P at constant temperature plus V. Again this term is not measurable, and for this term if we find this Maxwell's relation, then it is S P T V. Here S to P and so V to T. So this relation becomes del S by del P at constant T equal to del V divided by del T. Here P is constant and SP negative sign means here. So instead of writing this one, it is a measurable quantity we can determine by means of experiment, and so this is minus T and del V by del T at a constant pressure plus V. So this is the second relation. So second thermodynamic equation of state is with this enthalpy change. So del H divided by del P at constant T, and this is equal to minus T into del V by del T at constant pressure and plus V. This one, the second thermodynamic equation of state. So in this case also, if we calculate the for ideal gas, then this you can find by yourself del P by del T equal to 0. It means that H is a function of temperature only for this ideal gas. For Van der Waals gas, it is very difficult to calculate, but for this Van der Waals equation, del H by del P at constant temperature equal to B minus twice A by RT and plus 3AB divided by r square t square. I shall show this one while discussing the Joule-Thomson effect. Joule-Thomson effect. So in this case, it is found that H is a function of temperature and also the pressure. This term could also be expressed in terms of alpha. Say alpha equal to 1 by V into del V by del T at constant pressure. So del V by del T at constant pressure, del V by del T at constant pressure equal to alpha V. So inserting here del H by del T at constant temperature equal to minus alpha T V and plus V. You can get this V common 1 minus alpha T. This is also expressions of this del H by del P at constant temperature for any substance whose alpha is known, whether it is solid, liquid, gas. Alpha is known, temperature, volume is known. So del H by del P you can calculate. So this is all about this Maxwell's relations and its applications. I will give you one problem. Problem is that, say, the problem 1. Problem 1. So that the total differential of entropy in terms of temperature and pressure and volume can be expressed as ds equal to Cv by T dt plus alpha by beta and dt. And this problem has been set in UPSC, Union Public Service Commission 2001. And the solution to the problem could be done very easily. Say S is a function of a temperature and of volume. So ds equal to del S by del T at constant volume into dt plus. And here del S by partial differentiation, del V at constant temperature into dt. But here this relation we can get this S P T by Maxwell relations, S to V, then P to T. So del S by del V at constant temperature equal to del P by del T at constant volume. And this one already I have stated as alpha by beta. So this one equal to alpha by beta. And this value is, say, du equal, again du equal to d equal to TDS and minus PD. For constant volume, du equal to Cv dt and equal to TdS, and this term becomes 0 as V is constant. So del S by del T at a constant volume equal to Cv by T. So instead of this one, I can write this Cv by T into dt, and instead of this one, alpha by beta into dt. Another problem I can show, the problem 2, which has been set in the CSR UGC NET. Problem number 2. Maximum useful what associated obtained in a process is given by A. It is del H minus T del S, and B del U minus T del S, and C it is del H plus T del S, and D it is del U and plus T del S. It is a net CSIR UGC, as we said. So from these 4 options, maximum amount of useful work that will be obtained by from this one. Actually, in case of B is the right answer. Answer is B, and in that case, del U minus P del S equal to the maximum work done by the system. As the process is isothermal and temperature remaining constant. So this is third problem. This one the last problem, third problem. Among the quantities Q reversible in W, Q reversible by T, and Q reversible minus W, the state functions are A option, Q reversible by T, and Q reversible minus W, and B option, this Q reversible and Q reversible Q reversible and C, it is the Q reversible and Q reversible by T, and B, it is Q reversible by T and W. This one also set in net CSIR, UEC. So we know that Q reversible and W, they are not state functions. These are not state functions. So actually Q reversible by T equal to del S, and so this one del S state functions and Q reversible. Correct answer is A. And first one is del S and second one is del U. Q reversible by W equal to change in internally. Both these two are the state functions. This is not state function, so this one cancel. Q reversible B, Q reversible and Q reversible minus W. This one not state function, this one not state function, this one not state functions. So these three are cancelled. A is the right option for this. So this is the last discussions of these Maxwell's relations, and I hope the student can realize the importance of Maxwell relations and could also memorize from this trick that I have given. Thank you all for watching this video, and if you like, then please subscribe.